Okay, everybody, we're going to go ahead and get started here. So today is going to be all about vibration and shock testing. We're going to go into some guidelines of testing, as well as control strategies and fixturing as well. For those of you that don't know me, my name is TC Beinke, and I'm the National Account Manager for the testing division here at JACAN. So to start off, what is vibration? Vibration is defined as periodic motion of a rigid or elastic body about an equilibrium point. And when we're talking about vibration testing, specifically that body that experiences the vibration, we refer to as the DUT, or the device under test. And typically with vibration testing, we're going to be testing under one of the three mutually perpendicular axes, X, Y, or Z. So why do we perform vibration testing? The main reason we do this is to simulate stress from real-world vibration scenarios. This could be vibration from an automobile going down the road, experiencing rough terrain. That's a good example of real-world vibration scenario. And I've put some images here showing some other examples as well. We could be talking about vibration from machine operation, vibration from locomotives, or even vibration from aerospace components, and even wind itself can cause vibration as well. So I also want to go into just some basic vocabulary about the actual shaker system itself. So you'll see here I've pointed out a shaker in both the vertical and horizontal orientations. The armature is the moving member of the shaker, and this is what's actually going to transmit vibration into your fixture and your DUT. The armature is going to be bolted to, a lot of times, either your head expander or your slip table, whether you're in the vertical or horizontal orientation. And the point of the head expander and slip table are both essentially just to give you a larger working area to bolt your fixture or DUT to for vibration testing. So there's a few different types of profiles, both for vibration and shock. For our purposes today, we're going to stick with the ones that are most common that we run into most of the time. For vibration, this is sinusoidal and random vibration testing. And for shock, we're going to be talking about just classic shock testing. So let's go ahead and start off with sinusoidal or sine vibration testing. This is the simplest form of vibration, and the easiest way to think of sine vibration is to consider a mass and spring system. This mass, as it's supported by the spring, is going to operate along a sine curve. And you see here that I've put in a figure of your basic sine curve and pointed out some of the key parameters here. You'll see all the way on the right side, I've pointed out the displacement, which is essentially just the distance from the x-axis and the peak of that sine curve. A lot of times when we're talking about vibration, sine vibration testing, we actually refer to the peak-to-peak amplitude, which is just double the amplitude itself. Also, I want to point out the period, which you can see there on the left side of the figure. We're also going to talk about frequency a lot as we go forward, and the frequency is just 1 over the period, or the reciprocal of the period. I also want to point out that this would be an example of a sine dwell. So you can see here that all the parameters in this case are staying constant. Your displacement, your frequency, and your acceleration are staying constant as time goes on, and nothing's changing. We're going to talk about a sine sweep in a little bit here, and you'll see that that's not the case. We will have some parameters changing during a sine sweep. So why do we use sine vibration? Main reason we use sine testing is to find a resonant frequency. So a natural frequency of a system is the frequency at which that system oscillates when it's not subjected to a continuous or repeated external force. So it's the frequency that that system is going to oscillate at when it doesn't have any external vibration applied. And resonance is what occurs when the applied frequency equals the natural frequency. And the result of that is an exponential increase in the amplitude of vibration. So if you take a look at the figure I've put here at the bottom, this is a good example of what hitting a resonant frequency would look like graphically. You can see as the frequency increases and you do hit that resonant frequency, right at about 175 hertz, you get a huge spike in your vibration amplitude. So looking at this graph, you would know that the system you're testing has a resonant frequency of about 175 hertz. So usually when you're doing sine vibration, you're going to perform a sine sweep. That sine sweep is used to find resonance in either your DUT itself or the fixture. When you want to find resonance in the DUT, usually the reason that you'd want to do this is to see what kind of damage you're going to experience at that resonant frequency. So usually you would do a sine sweep over a specific frequency range, and once you find that resonance, you would perform a dwell on it to see what kind of damage your DUT is going to experience. The other case would be doing a sweep for fixture validation. And the reason that's important is you want to make sure that the resonant frequency of your fixture does not fall within the frequency range of the actual test that you want to use that fixture for. And if you look down here at the bottom, this is just an example of time domain data of a sine sweep. And you can see as time goes on, that frequency is increasing. So this is an example of what a sine sweep would look like on your actual vibration controller. In this case, and in a lot of cases with sine sweeps, you're going to start out with an increasing acceleration and a constant displacement until you reach your target acceleration. In this case, it's 1g. Once you reach that target acceleration, you're going to continue at 1g all the way up through your frequency range and then back down. I also want to point out the axes on this graph. You can see both the x and y axis are logarithmic. The reason this is so important is because it's going to enlarge small acceleration contributions. This is going to help them actually show up on the graph so you can see them. You can be sure that you don't miss any spikes in acceleration that way. Also, I want to point out that the x-axis here is frequency and it is proportional to time. So if you were to perform a sine sweep, you'd actually be able to see your shaker operating along that curve, and it would track along that green profile line from the left side of the screen up and to the right side of the screen to the higher frequency range. You'll see in a minute here when we go into random vibration, that's not the case. The x-axis is actually not proportional to time, and we'll talk about that a little bit once we get there. So random vibration oftentimes is used to simulate some sort of real-world vibration scenario, whether it be transportation or machine operation, any of those real-world vibration scenarios that we talked about a little bit at the beginning of this presentation. That's what you would use random vibration for. It's much more realistic than sinusoidal vibration, and that's because in the real world, the future of vibration is not predictable. So you need something much more random and sporadic to actually accurately simulate it. And you can see down at the bottom, I have put a figure of time domain data for random testing, and you can see it's very sporadic, especially when you compare it to a sine graph. Now for sine testing, the intensity is dictated by your G level or your actual acceleration. For random vibration, it's a little bit different, and the intensity is actually dictated by the GRMS. And that's essentially a measure of the cumulative energy input or a measure of how hard your shaker is really working. So to give you a better idea of what really is the GRMS, it's calculated just as the square root of the area under the profile curve. So you can see here, this is what a random vibration profile would look like on your actual shaker controller. And the square root of the area under that green curve, that's going to be your GRMS. Now, it is important to note also that while this GRMS does indicate your test intensity, two different curves with the same GRMS are not necessarily equivalent. They could have completely different shapes and different frequency ranges as well. So I want to talk a little bit about the X and Y axis for random as well. As I mentioned earlier, the X axis here is not going to be proportional to time. So rather than tracking along that green profile curve like we did with sine testing, with random vibration, at any point in time, your shaker could be operating at any point along that green curve. So it'll actually kind of bounce around that curve as you're performing testing. Also, I want to point out the y-axis. You can see for sign testing, it was just G's, it was just your acceleration. And in random vibration testing, we've got G squared per hertz. These units kind of confuse people sometimes, but essentially, when you take your acceleration, square it, and divide it by the frequency, you're essentially just normalizing those values. And this is important here because the acceleration during random vibration testing actually depends upon the bandwidth that you measure that acceleration at. So before you perform a test, the profile itself needs to be defined. And for random vibration, there's a few different ways of doing that, both graphically and by using a breakpoint table. And I've shown both examples here. You can see on the left, that would be an example of graphic representation of a random vibration profile. And it kind of speaks for itself. It gives a graphical representation of the actual shape of the curve itself. It gives you some key frequencies and accelerations. And then in this case, they actually gave you some slopes as well. And a breakpoint table, on the other hand, rather than giving you a graphical representation, it just gives you every single key frequency point and its corresponding G squared per hertz. And so when you look at vibration specifications and procedures, you'll see either a mixture of this or one or the other. So now I want to move on to mechanical shock testing. Shock testing is essentially used to simulate either impact, drops, or some sort of explosive force. The reason shock testing is so important is that shock excites all resonances. We've already talked about how important it is to test at resonant frequencies because you're going to get that increase in amplitude. And when you perform shock testing, each component of what you're testing is actually going to quiver at its own natural frequency. You can see here I've included a figure of a half sine pulse, and I've pointed out some of the key parameters here. You can see there's the amplitude pointed out there at the top of the curve, which is the acceleration level. And then I've also pointed out the pulse width, which is another key parameter. And that pulse width is essentially just the actual duration of the test itself. So you've already seen one example of a half sine pulse. And as I mentioned, this is the most common pulse shape. On the right there, you can see what that pulse would look like in an actual vibration controller. But there are other pulse shapes as well, other than just half sine, such as sawtooth, rectangular, and trapezoidal. And the trapezoidal shape, the sawtooth shape is what you can see there at the bottom of the screen. As I mentioned, half sine is the most common, but these days specifications are actually moving more towards sawtooth, and that's because there's a more realistic residual spectrum for sawtooth pulse shapes. Now, I also want to talk about the importance of including a climatic element in your vibration or your shock test. This can be especially useful for transportation tests. So if you think about having your part in the back of a truck, it's going to be bouncing around, it's going to experience vibration, it's going to experience possibly some shock, but it's also going to have some environmental conditions that are changing during this as well. So by including a climatic element in your test, it's going to help to more closely simulate that real world environment. And this is also really important because temperature and humidity can affect the actual material properties of your part. So if you're testing at a higher temperature, the material is going to be more more ductile. If you're testing at a lower temperature, the material is going to be a bit more rigid. And this could definitely affect the results of your test. This is just an example of our setup at our Greenville, South Carolina testing facility. You can see we've got our shaker there, and right behind it is our environmental chamber. So we can actually slide the entire vibration system into the climatic chamber, seal it up, and perform vibration testing with the climatic element as well, whether it be climatic aging or temperature cycling as well. So I also just want to list a few common specifications that we run into a lot for both vibration and shock testing. For transportation, you'll see I've pointed out a couple different ASTM specifications. Both of these we run into quite a bit, and they're both very useful because they give different profiles based on the method of transportation, whether it be air, ship, or truck transportation. Also, I've pointed out a couple of automotive specifications for vibration testing. That ISO specification is very useful. It's actually geared more towards automotive electronics, but it's oftentimes used for all types of automotive components other than electronic components. I've also pointed out an IEC specification. It's a great spec. It provides a lot of good guidelines for vibration testing, but it's important to note that it's more of a guideline specification rather than providing actual test parameters. So the IEC specification, as well as that military standard that I've posted there, the MIL standard 810G, both of those specs are going to require some tailoring on your end. And then, of course, OEMs tend to have their own specs for vibration as well. And oftentimes they'll actually reference back to one of these other specifications that I've already listed. So now, how do we actually measure and control our acceleration during testing? The way we do that is with accelerometers. And the most common type of accelerometer, the one that we tend to use all the time, is piezoelectric accelerometers. And you can see I've put a figure here showing the basic makeup of how these accelerometers work. And essentially, it's just a mass and spring system, with the spring actually being a crystal. And as that crystal compresses or elongates, it's going to generate an electrical charge, which is then converted back to acceleration by your vibration controller. And the reason we like to use these piezoelectric accelerometers is because they've got very high resonant frequencies. And this is really helpful because it means you can use these accelerometers for a wide range of vibration tests. One of the main downsides to these is that they cannot measure very accurately at low frequencies. So pretty much anything below 5 hertz, they're not going to be very accurate. Luckily, most vibration tests are going to be above that level. If you do want to measure and test below 5 hertz, you can use a capacitive accelerometer. There are some downsides to those accelerometers though too. For instance, they're not great at the higher ranges. So like I said, we tend to stick with piezoelectric accelerometers, but you really have to choose your accelerometer based on the actual test that you're performing. Now, accelerometers are only as good as where you place them. So you really want to make sure that you're controlling your acceleration as close as possible to your input vibration location. So you want to place it on the fixture itself, not directly on the table, and you want to have it near a mounting location and on a rigid member. One exception of this is, for instance, if you're performing transportation testing. For these tests, a lot of times there actually is no fixture. You're just placing the DUT directly on the table and letting it move about freely during testing. So in this case scenario, you actually would place your accelerometer directly on the table itself for control. Now, speaking of accelerometers and controlling vibration with them, there's a few different control strategies that can be used. Essentially, you can either control with one accelerometer or with multiple accelerometers. Most common control strategy is just single control. That's what we use a lot of times, and that's just using one accelerometer. But you can also use multiple, and there's a few different ways to do that. You can use maximum or minimum control, and the way that works is maximum controls based on the accelerometer that's experiencing the highest level of acceleration. And a minimum control does the exact opposite of that. And the reason you might want to do that is, for instance, let's say you want to make sure that no point of your DUT experiences a level above, say, 5 Gs if you're performing a 5G test. What you could do is you could place multiple accelerometers around your DUT. You could use a maximum control strategy, and that way you could ensure that no part of your DUT is going to go over that limit that you've set. The only downside to this is you're going to have some undertest. Certain parts of your DUT are going to experience undertest, and if you're using minimum control strategy, you're going to have the opposite issue. You're going to have some points of your DUT that are going to experience some overtest. Another option, if you're going to use multiple accelerometers, is to use an averaging control strategy. That takes a weighted average of multiple accelerometers, This can be useful because it does help to minimize the effects of spikes in acceleration, but it's important to keep in mind that an averaging method cannot correct for improper fixturing. So since we did mention fixturing, let's go into that a little bit. A fixture is really just anything that couples your DUT to either the armature or the head expander or the slip table. Fixtures can be extremely complicated, or they can be as simple as just using clamps. Now, the first question you're going to want to ask yourself when you're designing a fixture is, what type of material should you use? A lot of people think that the best route to go is to use steel because it's rigid and it's strong, but this is actually not the case for vibration testing for a few reasons. Steel is very heavy. When you're performing a vibration or shock test, you're going to want to keep your weight as low as possible. And also, steel has really poor damping characteristics. So if you think of hitting a steel object with a golf club, you're going to have that feedback back through the club and into your hands. And steel actually performs very similarly during vibration testing. It's going to ring. So if you do have to use steel, you're going to want to make sure you use it only at very low frequencies and for vibration profiles that are not very aggressive. So what you're going to want to use instead is materials that are lighter and that have better damping characteristics. And the go-to for that is either magnesium or aluminum. Magnesium is probably the best option. It's got great damping characteristics. It's very light. The only problem with magnesium is it can be pretty expensive. So a good middle of the road is aluminum. Aluminum is what we use in our lab a lot of times. It's a good deal cheaper than magnesium. It is a bit heavier, but compared to steel, it's still quite a light material, and it's still got very good damping characteristics. Now, the next question that you're going to want to ask yourself is, how am I actually going to join this fixture together? The best option in terms of preventing relative motion is going to be a fully cast fixture. Unfortunately, that's not always the most realistic option because from a manufacturability standpoint, it's not the easiest way to make your fixture. And you also can't change up the configuration. Say you want to use your fixture for multiple different DUTs. It's really hard to do that with a cast fixture. To use a welded fixture, to actually weld those components together. This is still going to prevent relative motion quite well. But again, you're going to run into that option or that problem of not being able to change up the configuration. It's going to be hard to use a welded fixture for different DUTs. If you do want a welded fixture, though, from a manufacturability standpoint, it can be a lot easier than a fully cast fixture. But you want to keep a few guidelines in mind. You want essentially you just want those welds to be very thick. You want a thick bead size that's actually equivalent or greater than the actual material thickness that you're using for your fixture. So then your next best choice is to actually bolt your fixture together. Technically, this is the poorest choice in terms of preventing relative motion, but it's your best choice if you want a fixture that's going to be able to be switched up for different DUTs, and it's what we use a lot of times. And it's fine to use a bolted fixture, but you do want to keep some guidelines in mind. First of all, you want really tight bolt spacing. You want to reduce that distance between bolts as much as possible, because as you reduce that distance, you're going to increase the resonant frequency of the fixture itself. You also want to counterbore all holes, and essentially this is just reducing the free length of the bolt itself. And the reason this is important is because, believe it or not, during vibration testing, the free length of that bolt is actually going to stretch a little bit during testing, and of course that's going to allow some relative motion. So you want to counterbore holes to reduce that length as much as possible. Another issue that you could run into with bolted fixtures is, since we're using relatively soft materials for your vibration fixtures, you might be concerned about bolts actually pulling out of the fixture itself. So one thing you can do to help mitigate that issue is by using stainless steel inserts, and that's going to give you something more rigid to actually thread your bolts into. So these are just a few examples of some good tried and tested vibration fixtures that we use a lot here at J.A. King. The one on the left here is a bookend fixture. Bookend fixtures are very useful because it's a relatively simple design. They're quite rigid, and you can use a bookend fixture oftentimes for a lot of different DUTs. In the middle, that's a basic cube fixture. Cube fixtures are also very useful because, again, it's very rigid. It's a relatively simple geometry. And cubes are also very helpful because you can utilize the different faces of that cube. So if you've got vertical and horizontal testing that needs to be performed, a lot of times what you'll have to do is rotate the entire drum of your shaker. And if you're using a cube, you actually don't have to do that. You can just bolt your cube in the vertical orientation, and then you can move your DUT around to different faces of the cube, and that way you've reached all three orthogonal axes without having to change up the orientation of the shaker itself. On the right there, that's another example of a cube fixture, but the difference here is that there's actually been some holes bored out of the cube itself. And the reason for this is to reduce weight. A lot of times those cube fixtures can get pretty heavy pretty quickly. So an easy way to reduce the weight is just to bore out some holes. Unfortunately, once you bore out holes, you're going to run into some issues with rigidity. So a good trick to keep up your sleeve is you can actually squirt damping foam into the voids of that cube, and that's going to increase the damping properties of the fixture itself. Now, it's important to keep in mind that it's not going to actually increase the resonant frequency of your fixture itself, but it is going to help to decrease the amplitude of the response when and if you do hit the resonant frequency of your fixture. So I also just want to point out a few guidelines when you're designing fixtures. You're going to want to avoid clamping when possible. I did mention clamping earlier in this presentation. We do use clamping sometimes, and you can use it, but you just have to be careful when you use clamping. You want to make sure that you use it mostly for tests that aren't very aggressive, and especially tests at low frequencies. And if you do clamp, you want to make sure you take note of the exact placement of those clamps. That way you've got a good repeatable test. And if you need to rerun anything, it's easy to do so in the exact same configuration that you ran it initially. You also want to make sure that you keep your center of gravity as centered over the shaker as possible and as low as possible. And this is going to help avoid causing any moment on the actual shaker itself. So this is just a quick rundown of what our capabilities are here at J.A. King at our Greenville, South Carolina testing facility. You can see I've pointed out the force peaks for both shock and vibration, as well as acceleration for both shock and vibration. Also, I've listed our max velocity there. For displacement, I do want to point out that 1.5 inches is per direction. So if we're talking about peak-to-peak displacement, that would actually be twice that, so it would be 3 inches. Our max frequency is 3 kilohertz, and the head expander is 4 by 4 feet, and that's actually the same side for our slip table as well. However, if we need to reduce weight at all for your test, we can actually create a fixture that's going to bolt directly to the armature rather than utilizing the head expander at all. So that's all I've got for you guys today. I'd like to go ahead and open it up for questions now. If you've got questions, you can, as I mentioned at the beginning of this, you can type them directly into the chat, or if you want them to be anonymous, you can send them to Lisa Messenger directly. Lisa, do we have any questions?
I have a couple for you.
Okay.
Someone wants to know, what is the max payload of your shaker?
Okay, so the max payload for vibration or shock testing for our shaker is actually a bit more of a complex question than you might think, because the actual weight of your DUT and fixture combination is not the only parameter to consider. It's also dependent upon the actual profile that you want to run as well. So what I like to say is if you know the weight of your DUT and you know the profile, you can always send that information over to us, and we can put that into our controller software. And that way we'll get a green light on whether or not we can go ahead and run your test. And if the fixture and DUT are over what we can perform with that specific profile, we can talk about changing up the fixturing configuration as well to help reduce weight, or we can potentially even take out the head expander and just bolt directly to the armature. Any other questions?
Yes. What temperature range can you do vibration at?
So we can go up to 170 degrees Celsius, and we can go as low as negative 40 degrees Celsius for both vibration and shock testing.
Do you guys do any of your own fixture designs?
Yes. So if you guys have your own fixture and you'd like us to use that, we can do that for you. We can even help you validate that fixture too. If you want to send it to us, we can do a sign sweep and make sure it'll work for the test. Or if you'd like us to just completely handle the fixture design ourselves, we can do that too. You can feel free to send us over CAD models or drawings or even the part itself. And then we can go ahead and design the fixture, and we'll perform all the fixture validation that's necessary before testing as well. I appreciate everyone joining us today and hope you learned a little bit something about vibration and shock testing.